They agree. Of course, GTTP would not exist without Rosa and her colleagues here in Portugal, and her. Like this. Gee, I can't wander around. I was going to go walk into the audience and get comments. Okay. Yeah, as I started to say, GTTP would not exist without Rosa and the huge and enthusiastic and skilled Portuguese Hands-on Universe team. So let's give Rosa and her Portuguese local organizers a huge round of applause. Yeah, there's no one like Rosa. So, again, we've been at this for a number of years, and the project has evolved. I mean, we always wanted to work with teachers, but then we soon found out, well, none of the software is any good for teachers, so we started developing software. Then we found, telescopes weren't working for teachers, so the telescopes have evolved. The planetarium programs, so piece by piece, these huge technological issues and organizational issues have fallen away, and I think we've never been poised in a better situation for rapid expansion. I think we're right now, I'll be particularly emphasizing our desire to build up evidence of student gain, but that's starting to happen. I mean, anybody who uses Hands-on Universe in the classroom knows it works in fundamental ways, and the students are learning better. We don't have hard data on this, but it's not that hard to get. So I'll share some of our own work on that. Let's see. Now, is there a clock on the screen here, just so I don't? You can give me a 7-minute warning, or? Okay. Anyway, so again, we started off, with classrooms in the United States kind of looking like this, sort of a 1984 vision of students all lined up memorizing formula. And indeed, I think that's still the case, even though kids might be moving around a little bit more. In education systems all over the world, we know inappropriate ways for kids to learn are being forced on them. And this is a terrible way. Just look at a Hands-on Universe classroom. It's kind of interesting. People from industry, and particularly in California, say, well, what do we want from our kids? Well, we want them to work in groups. We want them to innovate. We want them to talk to each other. We want them to communicate to other groups. These are kind of skills that people from industry want, yet you're not going to get that in normal teaching, which is the bulk of the world, particularly in developing nations where they're trying to copy the industrialized goods system. So I think in some ways there's particular GHOU and GTTP's efforts of trying to work with developing nations enables kind of a leapfrog system, in that we're trying to bring in what we think are to share, get resources from them, in our collaboration, best teaching practice, best learning practice. So again, and these classrooms that use HOU are so fantastic. Any teacher knows this. Again, some of you don't know what global Hands-on Universe are. Most of you do, but so I apologize to those who are experts in GHOU now for my talk. For the rest of you, I'll apologize after my talk. So, but anyway, what are we? We're hands-on. We're great teacher workshops. We're inquiry-based, great software, real and remote telescopes, including databases, the emerging databases of astronomy. We have students doing things. We're up to about 1,000 asteroids being discovered by high school students. Turns out these big asteroid surveys, or big sky surveys, turn out asteroids like crazy, and there's not in the survey teams, they're willing to share a little bit of the sky. And we find in 4 minutes a week of the Pan-STARRS survey system, we can find 100 or so asteroids. And we have 6. This is largely the work of Patrick Miller. This is a GHU affiliated project. And we have 6 asteroids named after high schools now. Our goal is to get an asteroid named after every high school in the world. I think that's something, and that kind of, I think that's generally a deep philosophical thought. We have some high school in some place in a country we can't even predict, and there's an asteroid named after that school. I think that elevates society. Okay, keep going along. Roger and Martine have seen these slides, so they don't have to. Okay, so you look. I'm so impressed with the agenda for the JIHU meeting. I mean, the richness and diversity. I feel a little embarrassed speaking to you. I mean, there's so much good work in this collaboration. The kind of efforts, people putting themselves into classrooms all over the world, developing resources and meta resources, sharing this, and again, particularly in the United States, we particularly benefited by work from the European Union. Our software, there's Salsa J, Stellarium, et cetera. All those were done right and well within European Union grants. In fact, there's kind of initially HOU started off well funded by the U.S. National Science Foundation. President Bush killed education in the National Science Foundation largely. President Obama didn't bring it back. But so in truth, I think a lot of the larger institutional funding has switched to Europe with the European Union. That's done a lot of good things for us. So that's maintained us. And I'm going to actually try to be actively fundraising with private foundations for JIHU too. The United States has a tradition of companies funding global projects. So it's clear, we can pay for people to come here and run, have a better run organization. So anyway, again, the key factor of global HOU is you, frankly, that you know how to work with teachers, you know how to talk to each other, you know how to bring best resources in. So, I treat with huge respect, the JIHU collaboration and all of you, and that's, without this team in this room and others, we really would be nowhere. So, again, some early JIHU people, you recognize Roger here, Alan Gould, Lek, and actually just an effort just to show, I don't want to oversell it because it's just beginning, but Susan Morbona, shown there with Rosa and Lech Mankiewicz, has found a potential site and a potential collaborator for a planetarium and teacher training center in Nairobi. That sort of just came out of this workshop. We think there are ways, people from Portugal can help, France, all over the world can help build this a state-of-the-art teacher training center for science education in Nairobi. And I think, actually we can do it really well with really have it teacher focused. Many planetarium, they're worried about cash flow and they kind of focus on a different audience. I mean, I appreciate that work, but I think this will be a very unique system in Nairobi, and we're going to all appreciate your input and ideas in building this. So, but Leonora's there. Vivian Hetty here, she just won Astronomical Society of the Pacific Prize for teacher education, which is fantastic. So, what's going on? Help. Did I sneeze on this? Again, and I think my personal and professional goals, and a lot of us really want to make spread success. I mean, it's different than a scientific collaboration where success is usually defined, on how well your experiment works and what the next project is, publications, blah blah. We have a much more distributed sense of success. The success is if we all succeed, and again, this is done by a lot of sharing. And again, I apologize. I think we probably have an official mission statement, but to my mind, we really want to help people get a lot smarter. Again, I think if people really do get smarter to a certain level, that will make the world a lot better in terms of climate change, war, proportionality, attacking other countries. I had a teacher we worked out, I think I shared this before, but the fact we're all star brothers and star sisters, it's a very powerful philosophical thought. And next time we want to bomb a city of civilians, we might think of that a little bit. All these people came from the same stars. And in fact, it's even a little interesting due to the fact, the atoms from stars come to Earth and then get recycled through the carbon system. All of us have about a trillion carbon atoms in us that have been in virtually every living creature or object in humanity before us. For the last 10,000 years, carbon gets cycled in and out of stuff. We have atoms of Julius Caesar and other luminaries in us right now. So anyway, I just think that the stars provide a wonderful kind of metaphor and a philosophy for the kind of work we do. And again, working together, all these, it's interesting. I think, we started off with just a few of the gears of HOU, and I think all these things are starting to fit together. We have, again, the telescope networks are working quite well now, the databases, the student work, still more pieces. I mean, we're still not totally near our mission, but a lot of stuff is there. So I was just thinking some of the examples of HOU implementation around the world. Just looking, I mean, what do groups do? Again, the most important is a core group of leaders in each nation. Absolutely essential. Without that, we wouldn't do it. And of course, we want to run workshops. These nations are all doing this, the outreach activities. Are you embraced by the government? Well, in Nepal, HOU, not yet, but I think eventually we will. I know Portugal is kindly embraced by the Portuguese Ministry of Education now. It's taken a while, but United States were not particularly well embraced by Department of Education. That's hard, but we are embraced by some school districts pretty well. So France is really extraordinary. Thanks to the work of Roger and Martine and the Fays, who will be here later, and French HOU. French HOU has activities that are in the high school, French National High School curriculum. They're in the exit test for French high school students, lycée students, and also in the teacher qualification exams. I forget what they're called, but you have to know HOU for all those, or aspects of astronomy. So that's been a real superb success in terms of government, something we can all strive for. So, I mentioned this last year, and it's actually gone quite well. It's a HOU implementation called After School Science and Math Integration. And this is where we do HOU activities based, but we try to emphasize big concepts. I think that's actually a nice lesson for all of us. If we have science standards, you must know planetary motion, blah, blah. If you have clear science standards, you can kind of mold the HOU so it supports what the kids are supposed to learn, but it's doing in a fun context. And for the United States, children of age 10 to 14 have to know ratios and proportions and linear equations. And actually, they came into HOU, they were just terrible at this. They knew nothing. It was so depressing to see how little they knew. I think they probably could memorize their way through certain tests. That's how they're taught. They're taught algorithms and formula memorization. But when we gave them these sample tests, they just were terrible. And also in the meantime, the United States has been trying to go to common standards, and the teachers don't know how to teach them. And the teachers are too busy. The textbooks are a mess, and the kids really hate math in the United States. A lot of kids hate math, I think, is a fair statement, the way it's taught, at least the students we were looking at. And so we had this program is pretty modest, just 2 hours a week after school, taught by Jennifer Prazo. She's going to talk about this later in the meeting, but I've been involved in it. Focused on proportions and ratios, And we gave, I thought this was remarkable. The gain, which is defined this way, your test, we're using agreed upon items for ratios and proportions from the national standards. They even after a 6-week intervention, they learned about half as much more than they learned before. So, I mean, this is in the United States, if you get a 2 or 3% gain in students' knowledge, you're a superstar. This kind of took nothing to do this, and I think that's a lesson in terms of. I know it's been done in many venues, but adapting HOU, so we're really supporting the national standards. I think this is kind of a wild thing, but children that age are so resistant of adult authority. They're always being told what to do, and they have computer programs running in their brains that I think really makes normal classroom-based learning a failure. And I think again that this, observing kids, they start to turn off the adult rejection thing, and they're focused on things. And we're really able to get new ideas and deep concepts, get them to learn by themselves new ideas and deep concepts. I'm not sure this is based on any educational research, but it sure is an observation. And I think it's a deep truth of learning that is ignored by 90% of the educators in the world. United States, they memorize, in fact, a lot of the world, memorize algorithms, the formula. Kids are coming, can dish out algorithms and formula like crazy, but they really have no conceptual understanding of what's going on or can apply it to word problems. And we show giving these students concepts and something they really liked, like astronomy, helping them learn these things, I think really proved effective. Now, also, again, part of our time here is to try to figure out how to work together. Rosa's helped develop the scheme based for GTTP based on the International Year of Astronomy. But I think now one of my personal goals is to try to oomph this up a little bit more with external funding. I think I know how to get funding now. And our system is very complete now. We know how to do it. And it's based on kind of a train-the-trainer model called JIHU. The lead teachers are called ambassadors, and they kind of fit in. Here we have, I don't know what JIHU is in Portugal. We have kind of leaders in each, quasi-leaders of groups of leaders in each of these regions. Asia, I think we'll have. Asia's too big to have one, so we'll divide up Asia. And this is a little bit of a mistake. These JIHU ambassadors will be trained in the respective continents. You don't have to fly them here every time. And then they can go to classroom teachers and hold workshops. And this is, in the United States, we reached over 1,000 teachers. I think we didn't have, we weren't able to follow them up enough and build enough community to keep them going steadily. That was I think we'd want to build in these ongoing communities wherever we go. And that depends on each nation too. Like, are teachers ready for that? So, again, this will happen. That this structure these meetings will be better funded. We can fly in people from developing nations and of course, they're being well run right now. It's a miracle. This workshop here has been funded on almost $0. So, but anyway, so we're going to do this. I think the future has never really looked brighter, and it's just an honor to work with such great people, and together I think we can really make a significant change in the world of education. Thank you so much.
Thank you, Carl. Hello, thank you. I'm Paulo Bretones. I'm very glad to meet you here, many colleagues and friends, and I am the chair of this section, okay? So because of the time that it was beginning, we have about 10 minutes of questions.
Oh, wow.
Yes.
We should probably repeat the question. Paulo, can you?
I just noticed that with your global ambassadors, there was no Australia, and you had just about everywhere else. So
Actually,
was there any reason for that?
I can't work Microsoft, what's it called? PowerPoint. Australia's in there,
Oh,
and
there's
we've
an
had a lot
Australia
of...
in there, I just,
Yeah,
okay.
we actually some recent, we're open. We've worked in Australia for 20 years, and with various successes in various regions, particularly in Queensland. There's been some good group. You're from Australia?
Yeah, I'm from Perth.
Okay, yeah, and we've had a little bit of action with Perth Observatory, I think, which has gone up and down.
Yeah.
We have 2 telescopes in Perth, 2 HOU telescopes in Perth.
Yeah,
Yeah, let's talk.
that's okay.
Yeah.
It's all right. I was just thinking if you didn't have one, then it's a very good place to find an ambassador.
Yeah.
I'm sorry that we have only 2 minutes because of the delay of the first,
What?
first
What the heck?
talk. Okay. Correction.
Well, the main. Oh wait, here's a. Please, somebody ask a question, please. What if I ask one to myself?
I have a question. No, I'm wondering, you've been doing this for over 20 years, 25 years, and GHU keeps growing, but all the education systems in the world are different. In your perspective, how come a system that was created, modeled in the US, can be adaptable to so many countries?
Well, I think it's intrinsically it has to be adopted to the country in whatever way it works, and so we're not forcing any adoption template. I mean, except made teacher workshops is what we ask for, and the software. So it comes with very few requirements in terms of copying the U.S. model. We never intended that the U.S. model would be implemented anywhere else, and also I think it's the conceptual purity of astronomy. I mean astronomy is a big thought, and everybody loves astronomy, just about it. I mean, many teachers, I should say, and all students, I think, love astronomy. So that supersedes any initial framework or any one educational system.
Thank you very
Okay,
much.
thank you.
Okay, next speaker will be Pamela Gay. Science Everywhere, Teaching, Inquiry, Learning as a Way of Life.
Good morning, everyone. I'm kind of surprised there's anyone in the room because there is an amazing session on Rosetta Science in the other room. So I'm going to be talking about it got shrunk and I lost a button when it got shrunk. There we go. So I'm going to be talking about how we contextualize using inquiry learning. We, as people who teach science in a variety of different ways, are all used to a model in which we teach science as we're looking at the how, the which, the why, the where, the what, the who. We're constantly trying to get students to look at things and build hypotheses and put things together. And it's often put into a big inquiry cycle. And the question when you're putting together a new curriculum, a new scenario, is how does it fit into this particular picture? This is the picture that's getting used by Go Labs. It's only one of many different representations of the inquiry cycle. And it's starting to get to the point that the question often isn't, what all are you teaching? How does it fit into the facts, the issues that it takes to make someone scientifically literate? The question is strictly, how does what you're doing fit into the inquiry cycle? And sometimes this leads to us forgetting that learning falls into a whole taxonomy of things that have to occur in the student's mind. One of the early results from astronomy education research in its latest renaissance was Bloom's taxonomy that looks at how students learn, and this is typical students. If you're dealing with gifted and talented, it actually gets reordered a bit. How your typical students pick up understanding. And what we find is, in general, students need to have basic knowledge. This is the vocabulary terms that they have to memorize. This is the historical dates, the historical context. And once they start getting basic facts, you start saying, okay, so here's how the facts fit together to build an understanding. Then you apply that understanding to new ideas. And then you analyze, so how does this understanding work? And you build your way up to eventually being able to create hypotheses. I can't say that word correctly, but you know what I'm trying to pronounce. And it's that creating of ideas that's actually the final step, the top of the pyramid of how you internalize new information. And people talk sometimes about how with inquiry-based learning we can do what's called backward scaffolding. This is where we have students go out, do an experiment, try something, hypothesize, do an experiment, try something, evaluate whether it works. And by starting from the experiment, they will build everything else for themselves. Now, the problem with having our students go out and simply practice by rote the inquiry cycle is, and I love this site and have to give full credit to Stephen McRae, and I'll tweet out a reference to this later. The problem is practice makes perfect is what we're constantly told, but practice doesn't make perfect. Practice teaches people to repeat the same mistakes over and over again. So if you have your students over and over and over practicing a skill without doing more than simply practicing that initial idea, they're going to pick up bad habits, bad ideas. This notion that I often find in our students of, well, there's only one correct outcome and I have to fit everything in, and if there's something deviant, I'm going to do it wrong. We need to give them a context to do their practice so that it's not just practicing the same skill, but it's building knowledge by immersion into a topic. We have to teach them skills. And we have to recognize teaching skills isn't inquiry, but it's required. Occasionally, you'll run across lessons labeled as inquiry where they have the students going outside, looking through a telescope, and making a sketch of Mars, of Jupiter, of Saturn. Practicing a skill of observation is not doing inquiry, but it starts to get there. We have to teach the students the skills. We have to tell the students, let's start by watching, let's start by looking. Because only by looking can you start to build the hypothesis. And then once they've learned the skills, we don't make them practice the same skill over and over. We start to innovate. Picasso said it best, bad artists imitate, great artists steal. The idea behind this is we don't want people to merely replicate the same thing over and over and over again. We want them to see, here is what a good example looks like. Here's what another good example looks like. Now let's improvise on that. Let's build to the next step. Let's figure out how to take this idea to the next level. And it's that innovation, that evolution of the idea that builds into doing actual inquiry. A good way to look at it is a lot of us go out and we curse different things as being cookbook science, where you give the student the recipe and you say, go out, do this exact thing, and when you're done doing this exact thing, you will have the perfect result. Here's one example, the go out and make something that explodes. This is what happens when you put certain candy into soda. You get foam billowing everywhere. And this is awesome, but this isn't inquiry. This is following the cookbook. And when we're making someone into a great cook, we're not teaching them how to follow recipes. We're teaching them how to innovate their own recipes. And if you've truly internalized how to use the inquiry cycle, you're not following somebody else's recipe. You're looking and saying, I have the skills to put these different things together and innovate my new own idea. So let's work on getting rid of the follow this, follow this, follow this, and instead figure out, well, how do we do interesting experiments that are actual inquiry experiments? And following on the idea of cooking, it's simple to do this while cooking. Now, this doesn't help us as astronomers, but let's face it, it's a Monday morning, we'd all like a cookie. And the idea with this particular experiment was, well, let's make cookies and cook them for different durations of time and see which one's crispy. And then let's take into account, okay, we figured out that 10 minutes gets us the perfect cookie crispness, but how do we get the color right? Well, we have to take into consideration the color of our cooking pan. So these are actually cookies that are cooked on different color cookie sheets where the kids did inquiry to see what color cookie sheet cooked them a cookie the correct color. Don't try and say that quickly. And the idea here is the inquiry cycle is more than just going out, making a hypothesis, testing your hypothesis, circulating around. The first step is people have to go out, they have to observe, they have to, the way it's phrased here is catch a glimpse of beauty in its natural state, record its every movement, and try to create a hypothesis that can accurately account for what you see. You have to start with seeing what's there. And only once you've done that initial investigation can you start to build an idea. Then you have to take that thing that you've observed back to the lab, and you have to do your experiment, and you have to recognize, and this is something that gets left out of the classroom, most of the things you try are going to be wrong. Real inquiry is about failing over and over and over until you find the thing that is right. And when in our classroom we teach our students, here's what you do, oh, your hypothesis was wrong, why did you hypothesize something that was wrong? You must not have understood the science. This happens. Hopefully none of you do that. But the students I get in my university classroom have been taught if you don't hypothesize the right thing, you clearly don't understand the idea. That's not how we need to teach it. We need to teach students that you're a friend of failure. This is how innovation is done. And after each attempt, you have to evaluate why things worked or, as is most often the case, didn't work. And then you have to take everything that you've learned and evolve it. And the example here is science is an art, and we can learn from artists. The DJ goes out and he mixes together music from a variety of different artists to create something new and something better and bigger. And as scientists, the way science is innovated is we take small ideas and we grow them up by combining this idea from here, and realizing there's a unified concept. Inquiry is a way of viewing the entire world, of doing art and of doing science. And we need to get our students to understand how all of these pieces fit together. We can't just lecture at our students, though, and we can't just have them do inquiry. We have to get them to have role models to see how this works. And role models don't have to be living, breathing people in front of their students. Sometimes you just step back and say, okay, let's look at how we know what we know. Let's look and see what was the inquiry that was done before, and let's see if we can build on this. So the example that I like to use is to look at the cosmic distance ladder. This is a way that different ideas are pieced together so that we can step from understanding how far it is to the moon, to Mars, to the Magellanic Clouds, and on outwards further and further across our cosmos. And the way that we were finally able to step outside of taking parallax measurements to measure distances to distant galaxies was to use Henrietta Leavitt's work using Cepheid variable stars as standard candles. And for those of you who don't know the story, this hard to see in a room this brightly lit picture shows the large and small Magellanic Clouds. These are only viewable from the southern hemisphere, and she was using glass plates that are now stored at Harvard College Observatory and that were taken at the beginning of the last century. And as she was going through these glass plates, looking at the brightnesses of the individual stars in the large and small Magellanic Cloud, what she realized was there was this relationship where the stars that took longer to vary in brightness also had a larger average brightness, and the stars that varied in brightness more quickly had a smaller average brightness. And she could adjust back and forth where she had the same straight line for all of the stars in the large Magellanic Cloud, all of the stars in the small Magellanic Cloud, and she could adjust it with a constant offset to bring the stars from the two clusters to match. And she realized this is a way to measure distance. You can teach your students this example of what Henrietta did, and then say, okay, let's look at something similar but different. Let's look at Arillary stars and globular clusters. Let's see, how does their period and luminosity vary? How does it vary between different clusters? What are the different characteristics between the clusters? And you can get your students to realize that with these little stars, it's not a period luminosity relationship, it's a metallicity luminosity relationship where all of the stars are essentially the same brightness no matter what their period is. It's the metallicity of the system that creates small variations. And you can have your students improvise on Henrietta's results to get at new science. So you're teaching them this is how it was done. Now let's look at a bunch of data from other systems. Let's figure out how we can build, how we can innovate on these earlier results, and how we can basically build out on this cosmic distance ladder. It used to be a whole lot easier to get students to understand inquiry because when people's cars broke down, they stuck their head under the hood and tried to figure out how to fix it. I don't know about you, but I remember watching my dad and my grandpa argue over, well, if I wiggle this, maybe it will start. And they wiggled lots of different things, and sometimes they actually did get the car to start. What they were doing was they were hypothesizing this is where it's broken. They were testing their hypothesis. They were evaluating whether they were right or wrong and usually cursing at the car. And this was the authentic inquiry cycle put into real-world examples. Nowadays, people don't fix their own cars, they don't fix their own computers, you just buy new things or take it to the mechanic or the help desk at the computer store. But we can still refer to this frame of reference because most of us have seen someone in our lives fight with their car when it wasn't working. And we can get kids thinking this way so that when kids start having conversations about, well, maybe we could, maybe we should, they start thinking in terms of inquiry. I want to do this. How do we get this done? Well, we could try this, we could try this. Let's try both and see which works best. We can introduce this idea of inquiry into their everyday conversations. And we can start getting them to think about what are the real world ways that you can use this. We've all had that moment of expletive, where I'm standing, I don't have good wireless signal, and this is where I need to be to do something. Well, you can get your kids trying to figure out how to get the wireless signal where you need it using dishes and aluminum foil or Pringles cans. You can help them figure out how to solve the modern day problems that we deal with on an everyday basis and encourage them to bring inquiry into how they think. It all comes down to trying to put the pieces together. We have to remember that Bloom's taxonomy. We have to remember you teach them facts, you teach them ideas. Students need to know basic concepts before they can start doing inquiry on the basic concepts. Once you get them the basics, give them examples of how information has been derived. What was the inquiry cycle that some professional scientists did to get us to the understanding we have today? And then you can work on getting them to innovate on top of those ideas. There have been some great ideas that have come out of all different places. This is one of my favorites. It's really hard to take photos of stars that show the stars' colors clearly. You look at a picture and you're like, yeah, that's kind of blue, that's kind of red. But when you take the photo out of focus, suddenly it's easier to see the color because it's spread out over a greater area and you have less problems with saturating your film or saturating your pixels. This is an example where someone's like, okay, I'm going to get it in focus, cover the front for a few minutes while the sky rotates, and then slowly drift my camera out of focus until I can clearly see the colors of the stars. This is a neat idea that gets someone combining different ideas about saturation, about color, and eventually putting all of these different pieces together. One of the things that we often talk about is how those different colors of the different stars actually are related to the fact that each of those colors means the star has a different temperature. Now, this is a really hard concept to get across to our students. And the thing that we usually do is we start throwing maths at them and start asking them to do the temperature diagram of here's where the peak wavelength intensity is for an object of this particular color. But that's not how the original scientists made this discovery. You can go back and tell them about how Herschel discovered infrared radiation because he had a thermometer and he set it down next to the rainbow created by a prism and it heated up. And he measured a temperature greater than room temperature because the infrared light was hitting his thermometer. And you can actually recreate this by sticking a thermometer in the different colors of the prism. And you can show the kids tangibly that different colors are different temperatures. And sometimes you can do that cookbook science, and you can innovate on top of the cookbook science. One of the things that more and more people are starting to do is getting kids not just building optical telescopes like the Galileo scope or any of the paper towel tube telescopes that are out there. They're also now starting to build radio telescopes. There's the Radio Jove project, the Itty Bitty Radio Telescope project. These different projects vary from having people building the radio telescope from the ground up, like is shown in this picture, to taking your direct satellite dish that you might use to watch television and taking it apart and redoing how it is hooked up to electronics so that you can use it to study the radio sky. Well, with projects like this, you start by following a cookbook recipe. And you use that experience by following somebody else's instructions to figure out the basics, to learn from somebody else's example. But once you get there, you can do what actual scientists do, what actual instrumentalist do, and you can start fussing. You can say, well, if the chicken wire works, maybe if I used something else it would work better. What happens if the spacing between the wires is smaller? What happens if it's bigger? What happens if I use different types of solder to hold this whole thing together? You can get your students taking an idea that's already good and then doing what, well, all of us do, and taking that good idea and trying to make it better through innovation. This helps kids understand everything they do can be improved, and they can do that improvement themselves. So I've basically instilled a philosophy on you, I hope. We know that inquiry-based learning is, from research, the best way to go. Hopefully all of you have read those papers. What we need to do is take it to the next step and get students seeing that inquiry doesn't just belong in the classroom. You need to take it outside, look at the sky, look inside your car, look everywhere, and see how you can innovate the world around you. Thank you very much.
Thank you, Pamela. We have at about 10 minutes for questions. Okay? Okay, Mike.
So you mentioned historical examples many times, and I've found, I'm big on the history of astronomy, and I'm involved at a historic observatory, and I use that history to teach the students who come to the observatory for our special programs. And I'd like you to comment on the value of history. It's sort of cookbook to repeat what people have done before, but in a sense it's just a guideline. A lot of time, my feeling is you can't really understand your field unless you know the history of how you got there in the first place. But a lot of times I tell students about the history, maybe with a 100-year-old telescope we're using, and they said, they did what? You know, they don't understand. So this kind of breaks the ice, gives them something to follow, try and repeat. I don't think it's really cookbook, but at the same time, you don't have to start over. So I want to see your thoughts on it.
So the basic idea is we want people to know not just what we know, but how we know what we know. And the how we know what we know, well, that's clearly something that didn't happen this second. It's something that happened in the past, whether it be earlier today, Rosetta set back one set of information, or over 100 years ago, we started figuring out how comet tails work. Everything that we know now, someone in the past has figured out. And teaching our students all the crazy ways that people have innovated our current understanding helps them get a better perspective on how to do science. For me, the best example of this is how neutrons were discovered, because I don't know how they got the crazy notion they got. They basically had something that was giving off these weird particles. They knew it was giving off these weird particles. They didn't know that much about it. And someone decided to stick a block of paraffin in front of a beam of what we now call neutrons. And paraffin has loosely associated protons in it. So when the neutrons hit the protons went flying out because of conservation of momentum. They could look at the velocities and they could tell these two things had the same mass, one had charge, one didn't. How you decide to randomly throw a block of paraffin in front of your particle stream is one of those things that will leave me scratching my head for the rest of my life. But in telling this sort of thing to our students, it opens up the box and says, it's worthwhile to try all of your crazy ideas, because sometimes your crazy ideas will lead to discovering the neutron. So it's extremely important to give this historical information, to get the students sometimes recreating, as long as they understand they're recreating, and then get them to improvise on that to try and see how they can evolve the knowledge from the historical data.
Thank you. Another question? There.
Thank you for a very interesting talk. I have two questions. One is about improvisation, and the second is about the arts, which you mentioned. Mm-hmm. You touched several times on the issue of improvisation, and I couldn't agree more. The question is, I see improvisation as a skill in itself, and maybe even as a state of mind in itself. Do you think that it is necessary and or possible to teach future teachers the tools that they need in order to improvise? And if so, could you try and share with us your imagination of what such tools may be?
I don't actually have to use my imagination on that one, because I've seen how they train planetarium instructors. I went to the Southeast Planetarium Association meeting earlier this summer down in Florida in America. And one of the things that they had the planetarium people doing was improv, where they were taking the ideas from the Whose Line Is It Anyways television show and getting people to work in that same context. So, for instance, how many times have you heard someone say, yes, but? Which you know is going to be the moment they say why they can't do something, how they can't do something, and that doesn't work. And so the example they used is you're in a management meeting, you're trying to figure out how to get your planetarium collaborating with other people in your university. The second you say yes, but, people turn off. So let's improv on how to do yes, and use the word and to get your ideas across in a way that people understand. And so they were throwing out all sorts of, okay, you and you, go, and giving us ideas on different scenarios that weren't our personal scenarios, so we weren't emotionally going to get hurt, but we were practicing these improv skills. And I think simple things like teaching people to always do yes and always build on one another's ideas. These sorts of watch whose line is it anyways and apply it to your classroom. Teachers need to be doing that so they know how to turn on minds instead of turning them off.
Thanks. And another short one, if I may. You said
okay.
something, it's a very short one. You said something about the arts in inquiry. I didn't jot it down, but I would really like to, with your permission, if you remember it or something similar about how inquiry is a meeting point between art and science or something.
We have to see science as another art form where creativity is important. And the best way to look at this is when we're looking to combine ideas, we need to learn from the DJ. And as I said, I'll tweet out the link to the cartoon I found last night that said everything I wanted to say in this talk. Where we take a variety of different excellent ideas the same way a DJ takes a variety of different songs, and we combine them to create something new and innovative.
We have more 3 minutes. 3 minutes. Do you have any question? Mike, again? Okay.
Okay, 2 of you listened to my talk, clearly.
I wasn't going to wait for the microphone, but because there's a new generation of youngsters in my family now, it seemed to me innovation is kind of rare, that we, as we get older, we learn not to do that hands-on inquiry, but when you're 2 years old, that's the only thing you do. That's how we really learn. So, I mean, is there a sense that we're just trying to return to what our actual nature is? Because it seems to me hands-on or inquiry-based is how we're wired to begin with.
All of the research into inquiry-based learning basically says the best way to go about learning, and this is a proven technique in medical school, which is kind of the most important place for somebody to absorb all the information they're taught. You need to watch something, you need to do something, and you need to teach something. And the idea here is you watch someone do a medical procedure, you then try the medical procedure, and then you have to talk someone else into going through it. Now, when you're talking, that's often where the innovation comes from. The ideas get shared, they get built upon. When you're a little kid, you watch the adults around you do things. You then try doing it yourself, and then you'll go and do, "Hey, Mom, look at what I figured out." What we do as small children that we're naturally wired to do, unfortunately, we often get unwired for through the educational process, where we're taught you have to get the right answer, you have to get the right results. If you did your lab and didn't get the right results, we're not going to say, let's figure out what's wrong with the equipment. We're going to tell the student that they're stupid and wrong. And so we need to figure out how to roll it back to being that 2-year-old and roll it back to how do we do the, "Hey, Mom, look at what I did," and turn it into journal articles. And this is what the medical field has gotten very good at. And we need to figure out how to do the same thing with the rest of the sciences.
I think that we have no time, but we need 2 minutes to prepare the next presentation, okay? Instead of this, I would like to thank you very much, Pamela, for the nice presentation.
Isabela, onde é que está? X. X é cá para o fundo. Ok.
Do PDF. Eu vou PDF.
Queres o PDF?
Sim.
Não queres o PTT?
Não desformato.
Ctrl C. Vamos pôr aqui já dentro da pasta. Rosa, ¿dónde está?
Sos Portugal. El PDF.
¿El PDF también?
Sí, ya está.
Okay. To close it. De nada. Oh, stupid. Só que agora para apresentar ali. Para apresentar ali. Se calhar é melhor pôr ali. Vou arrastar para ali.
May I start?
Okay. Okay, let's start. The next speakers will be Isabel Borges. Okay, collaboration between non-formal learning and science curricular teaching.
Did you have a thought about it? I only started to think about it 10 years ago. Good morning. First of all, my name is Isabel. I'm Portuguese. Sorry for my English. I will try to do my best, and I'm here to talk you about a little bit my work also. I work in science centers since a few years, as I told you, and I'm presently at the planetarium Carlos Gulbenkian in Belém, which is a very nice area. You may visit it. And in this little presentation, 10 minutes, I will present you the context, the problem, and the questions, looking for answers, the methodology followed, some results, more examples, and some conclusions. So, the context, we all know about it. We mostly are teachers or we have contact with teachers. And we are worried about education. And education in this century is not absolutely the education in the last century. Many of you were born in the last century like me. Our models, our school classes were not and are not supposed to be as today. And something came up, a massive school education. Everybody goes to school. Everybody has to learn about sciences. This is great. Okay, this is great. It should be like this. But for the classical schools, it brought a big problem because they were not prepared and students were not all the same. They came from many different backgrounds and teachers had to adapt and schools had to adapt. And we are even today trying to adapt to this question, to this matter. So, what to do with science education? What do you want to do? What are you supposed to prepare? We all know, but we cannot forget it. We have to work for a democratic society. We believe in future generations with critical thinking citizens. And we want to have more science and technology. We like to have better lives, new drugs, new facilities, and so on. So, in Portugal, in 2011, the basis of the new curriculum were born with a legal dispatch, which say, I'm going to read it, the curriculum should focus on thematic content, enlightening the essential knowledge and understanding of reality that allows students to take their place as educated members of society. So, as I told you, more responsibility for teachers. And meanwhile, research is working on the field. And the main idea, which is not very comfortable for us, teachers, really what most people think, what is science and how does science work, generally is not the good idea. And it still is today, in 2014. And most of it what is not absolutely not comfortable, formal science education is limited. And we already know that classrooms and schools are not ideal, every one of them. So what to do? Let me just show you a little scheme for those who are not Portuguese about our formal education system in Portugal. We have from now 12, I think the last year it started the law, 12 mandatory years in high school, basic school and then high school. And then the purple color is only for university. So, as I was telling, the context and the nature of science, it has to be also respected for going forward with this issue of formal education, which is not absolutely great as it should. And one of the main important ideas of keeping in mind when someone teaches science to students in classrooms, big classrooms, different backgrounds, is to preserve absolutely the nature of science. And I remember Pamela's presentation because the nature of science was absolutely in it. The nature of science is the conceptual schemes that constitute the foundations of science. We are talking about the philosophy of science, the history of science, how science affects the order, how the laws are valid or not. Any law is valid until another one comes up. The discussion of ideas, the build-up of ideas, and the role of experimentation. You have to try to make sure you are thinking and doing okay. So, a challenge, it's not only for schools, but it was put up and cleared by the European Council in 2011 by a target for 2020. One of the trends and challenges of the next decade is the introduction of new forms of learning in an innovative school environment and the achievement of lifelong learning through formal education, non-formal and informal. Well, three kinds of education. Don't worry, the non-formal, it's a bit new here, but it's a kind of between the two, formal and informal. We are learning now, it's a kind of informal. You go on the streets, you're learning informally. You are in school, it's formal. But there are some places that are preparing experiences for making someone learning that is non-formal. So the problem, what is the contribution of these environments for the science curriculum? Because we are actually worried about the science curriculum teaching. Teachers have to accomplish their curriculum. They have to make reports at the end of the year saying, I teach science, but not freely. I'm teaching the science that the curriculum told me to do. So we tried to put up some questions more specific. Do students show greater enthusiasm and interest in science after these non-formal sessions? Do students have greater understanding about the important ideas and explanatory frameworks of science? And the third one, which is for examinations, did students learn concepts on the subject focused? Specifically, the study we did was about wave, sound, and light. So let's try if having non-formal sessions, and these students were a group that went to a science center, it was the Sintra Science Center, and they made 2 visits. They were prepared, they were sought, planned, and I'm not going to explain what is Ciência Viva network of science centers. You have a lot of them through the country. And the methodology was these 3 sentences. The teacher decides what to do. He has to prepare a visit at 3 stages, before, during, and after. He cannot put any of these apart. They all go together. And the Science Center is only a science teaching resource. So the art of the teacher, and he knows because he's trained for that, is to prepare it and make a connection between his classes and the resources of the Science Center. So the results we had were good. And we made a lot of experimental, we made many, instruments of researching. I don't know the name of all in English. They finally, after 2 months, 2 visits, 2 months work in school, they showed greater enthusiasm and interest. They showed greater understanding of the important ideas of explanatory frameworks of science. Most of them really improved their performance. And there was evolution of students learning about the scientific concepts involved, relationships, implications, and specifically applications, which cannot be forgotten in the teaching process, because they had to apply it in the science center in the second visit. I only show you more examples of studies made in science centers. Where do planets fit in? They didn't use numbers, but they end up for knowing absolutely where the planets were located around the sun. Proportions, mathematics, and space. Another one, teaching something that is frightening and it's not in the curriculum, but helps teachers understand what is physics about. And they really built up a cloud chamber, and they understood why the scientists had to discover more about the inside of the atom. And they also visited the exhibition and all the experiments they have. And one more, who said you cannot teach astronomy to blind and impaired and visually impaired students, with some tactile resources that were not built at the science centers, but actually they born in the 2009 International Year of Astronomy. They were developed in the University of Valencia by Amelia Ortiz-Gil and his team. So the goal was to create an image, and it was a success, also with some practical resources for classroom. And the conclusions of all this, which is 10 minutes, 30 seconds, just for making my conclusions. Learning science has become more accessible and attractive when communicated as a living and social experience. I'm going to quote Pamela again. You have to get inside, you have to emerge on science to understand it. You have to get the head of the action, and students do that in science centers. The sessions of non-formal educations are, I'm sorry for the undoubtedly, but they really are undoubtedly a complement of work in school, contribute to the development of the science curriculum, and contribute to the quality of learning and the success of our students. And we have a lot of stands for it, not only we at the science centers, but also of all of these organizations. And I mean, yes, people learn in informal learning environments by the National Research Council, the 3S in America, Board National Science in the United States also, as concerns for Europe, the Council of Europe, European Commission, Euroscience, and in the world, UNESCO. I'm sorry. Don't forget, I will leave you these 2 quotations, because then I will say goodbye, but I will leave time for reading the quotations and waiting. Thank you for giving more extra seconds, and I'm ready for your questions.
Okay.
Thanks. I was wondering if you could say something about evaluation of programs and how that's similar and different between formal education and informal education.
Yes, those studies, especially the first one, was rather complete, and it was done inside the Open University in Lisbon. And it had several scientists and educational and physicists, so it followed all the rules of real scientific research. And only for that we believe it is right and it is true, because all this empirical work now is done a little bit by our hearts, because we are working on this many years ago, from many years. But in the start, when Ciência Viva was born in Portugal, it was not born just like some wish. it was born because Europeans and Americans were studying how to improve science teaching, and many studies, especially in the United States, were made about science centers.
Okay. One more question? Nobody?
Was I so convincing?
Yes.
You have 20 science centers in Portugal.
Okay, Isabel, thank you very much again.
Thank
The
you.
next, so let's. Next speaker is Rosa Ross about science on stage, illuminating science education.
Okay, thank you. Good morning. I want to introduce some information about Science on Stage. This is a project that basically is a network for science teachers and for technology teachers at secondary and primary school. We begin to work in a European platform in order to exchange ideas, and also we try to promote the concept of science to the society in order to motivate young children and also to help teachers that they are interested to teach science in a different way. All the activities of Science on the Stage are from teachers for teachers. We focus on teachers, basically. And we are working from 2000. This project begins as Physics on a Stage, after it was open to all the science, and begins with a project by ISO, ISA, and CERN. After, in 2010, was created an association of teachers that the headquarters are in Berlin. Involved 25 countries, and also Science on a Stage is important in Portugal and also in Spain. I want to mention this relation because in the Science on a Stage Spain, that the name that we use is Ciencia en Acción, because the translation of Science on a Stage to Spanish was not so good. I have here some examples of our activities and some materials that we produce. We involve also teachers in Portugal. You know that Spain have 4 different languages, official languages, and one of them is Gallego. Gallego is very, very close to Portuguese. Then we involve and we accept to have participants from Portugal in Spanish editions. It is good in order to exchange information and exchange and to begin to know all of us much better. Now we organize essentially fairs and different conferences in Europe. This is a picture of the last edition of Science on a Stage. It was in Poland. In Frankfurt, Slubice. It is a small town just in the border between Poland and Germany. And then was an edition that mixed both countries to work together with all of us, of course, with all the 25 countries in Europe. Well, our events take place every 2 years. Normally, in the conference, in the meeting, participate 350 science teachers of primary and secondary level from 25 different countries. In order to participate in this event, it is necessary to participate in a national event previously, and in this national event is organized the delegation for the European activity or the European event. Then every teacher have one stand, and during the period of the fair, they have the possibility to exchange ideas with other colleagues. There are some hands-on workshops organized, talks, discussions, and some presentations. I have here the list of the last one, 3 editions. Was one in Copenhagen, the other I mentioned before, in the border in Poland and Germany, and the next one that will be in UK. Well, after each one of these events, normally we evaluate the results, and I have here some results related some questions that appears in the questionnaire. For instance, we obtained 69% of teachers that they recognize that this kind of meetings are very motivating for them, and they enjoy a lot to know different ways to teach science. The 74% of participants appreciate very well that the exchange of experience with other colleagues from other countries. The 79% of participants, they recognize that they use some of ideas that was presented in Science on Stage when they teach to their students. And the 50% of them also mentioned that they continue after the event with connection, with content, with some local meetings maybe, with other participants in the main event. The next session of Science on Stage will be in UK. In 2015, will be organized by the King Mary University of London. Our plan is to invite 350 science teachers from 25 countries. And the selection for each one country will take place this year, 2014, in each one country. For instance, I am the national representative or the chair in Spain, and our event in 2014 will be next month, the 3rd, 4th, and 5th of October. And well, in this case, we decide what is the members of our delegation. In Spain, in my country, we organize every year. Then our delegation is the result of the best projects in 2013 and 2014. All the people interested have 2 possibilities: to contact directly with the website, or if exists in the country a share or project, the Science on Stage, then contact with them and participate in the national event. Well, the activities, of course, that I mentioned was basically to exchange of ideas and new methods to teach science, but also we are interested between the 2 editions to organize other kind of follow-up activities that basically are in the 3 kind of them. Teachers training, that were organized in workshops or on other kind of activities in each one country. Teachers exchange, that it is possible to move teachers from one part of Europe to the other one, from one country to the other one. And also we prepare teaching materials taking in account the results of previous events that we believe that they are interesting. In this moment, for instance, exists a team of 22 teachers from 15 different countries that they are preparing materials. And in this moment, the last one brochure that was published include 11 units. And for instance, there is one unit related to space, and that was very well accepted for teachers, basically physics teachers and also mathematics teachers, because in some cases, in order to teach mathematics, it is so difficult to motivate the students. But if you introduce proportions that mentioned other colleagues before me, or trigonometry, or all of this connected with astronomy is always much more motivating for them. If you are interested to obtain information, you can send an email to this address or to contact directly with our website. In general, we are very, very interesting to involve more and more teachers. Then all of you are invited to visit our website and to contact with us. Thank you very much. And I don't know if there are some questions.
Thank you, Rosa. Couple of questions. Pedro?
Thank you, Rosa, for the presentation, also to let us know a bit more what is science on stage nowadays. And I was wondering, you saying that you want to bring the teachers to the science on stage, and that's the main goal. Who provides the funds for the teachers to come from the countries to the event? The countries need to raise the money, or you have a central budget so you can bring the best teachers and the most motivated ones?
Well, always the money is the problem, you know. Well, normally Science on a Stage give to all the teachers accommodation and all the meals that teachers need. But the transport to go to there, to pay the travel expenses, it depends on the country. Then, for instance, in my case, that I know much better, in Spain, we pay to all the teachers basically the travel expenses, not in a good way. This is only a cheaper way, but we try to give them this support. But of course, it is complicated for countries because it depends, but there are some delegations that they have maybe 20 members. To pay travel expenses for 20 teachers, it is not easy. But normally, the countries try to help totally or partially these expenses. But the accommodation, all the meals are paid by the organization, Science on a Stage organization.
Another?
Thank you. Is it end of June a convenient date for all teachers in Europe? Because, for instance, in some countries, there are tests for the children at that time. So, do you think of having this event later on, during summer period, for instance?
Well, the idea is that we are open to involve more and more countries, no problems. But if the teacher is a teacher that is working in one country that in this moment is not in the organization, they can contact directly with us, and we also can accept, it depends on the kind of project and all of this, no? Because of course that a jury revise it, but it is not a problem if don't exist Science on a Stage in this country. It is open also to the teacher.
More questions? Rosa, I have one. Very, very rapidly. Is it possible to continue the participation of each teachers, or only during the event? Do you have a relation with the time?
Yes, we have a relation. For instance, we invite from one country to the other country for workshops, something like that. We cooperate in some materials. The idea is to open a network for teachers, and they exchange information. In some cases also there are some projects involving students, of course, because when teachers work with the students, but basically our focus is on teachers.
Okay, thank you very much. There's no more questions? So we finished this first section. I think that Rosa have any information before the lunch, okay? Okay, thank you very much, Rosa, again.
Thank to all the speakers, but also for Paulo for sharing the session. It's a privilege to have you sharing our session. So just a quick announcement. We have now 2 hours for lunch. You all should have maps where you have signaled where the restaurants are. And in the afternoon, we restart at 2:30, okay? So see you all soon.